Thank you very much. This is going to be a celebratory lecture and no technicalities except to admire the extreme ingenuity of engineers and physicists to give us modern high-energy astrophysics. So when I was talking with Ramo, he mentioned the 50th anniversary of the publication of the paper on pulsars, but I also reminded him that we've also got the centenary of the birth of Martin Ryle, who was born in 1918. Now, as you all know, Martin Ryle and Anthony Hewish were awarded the first Nobel Prize for astrophysics. It was for radio astrophysics, and here is the citation here. You can see it, for their pioneering research in radio astrophysics, Ryle for his observations and inventions, in particular of aperture synthesis technique, and Hewish for his decisive role in the discovery of pulsars. And these really were very fundamental aspects which really convinced everyone by the mid-1960s that general relativity had a role to play in astrophysics. Before that time, most people said, yes, they're very beautiful constructs, but they were forced upon the community by the discoveries in radio astrophysics and the pulsars as well. So I will go quite quickly, but very clearly, with lots of pictures and no technicalities, so you can relax. So radio astronomy was born with Jansky's discovery in 1933 of the radio emission from the galaxy. That was followed up by an amazing piece of work by Groot Reber, who built his own radio telescope, which you see here, in his back garden. This is the sort of thing that one cannot do nowadays, but this was a leading telescope, and he plotted out for the first time the structure of the galaxy. And here's his picture, which appeared in Astrophysical Journal in 1940, and there you can see in the celestial coordinates clearly the galaxy. This was essentially ignored by everyone. There was one paper in Astrophysical Journal which simply said this emission cannot be radio Bremsstrahlung emission, nothing else. So it was more or less ignored. Now, after the war, many things changed. And in particular, there was a huge effort, particularly within the UK, to develop radar in order to defend ourselves against invasion. And almost all the physicists in the Cavendish laboratory, where people were working, went to work to develop the technologies in electronics, aerial design, cables, everything in order to protect the country. Now, after the war then, there was a huge excess of brilliantly trained people in electronics and all of these techniques which had been developed for radar. And in particular, in the UK, which had put this huge effort into this, in Manchester and Cambridge, there was a lot of work done, and also in Australia, where, again, one of Bosey, who'd been working on this as well, went back to Australia. Now, the Cambridge group was led by Martin Ryle, who was an extremely powerful figure. And here's a picture of the radio astronomy group in the early 1950s. And this is a quite amazing picture. This is the group of people who built all the radio telescopes with their own hands. So it is very much hands-on construction of these instruments. Now, the people there that you should note, here we've got Martin Ryle sitting in the middle. He was the first one to come back after the war to join the radio group in the Cavendish. And then Graham Smith joined him as well. Graham went on to become director of Jodrell Bank and Astronomer Royal as well. And then following him was Tony Hewish 1 year later. The other person I will point out on this picture is Peter Scheuer. I was, in 1963, when I went to Cambridge to join the radio astronomy group, I was supervised by Martin Ryle and Peter Scheuer. That is what one calls growing up very quickly, very fast, between two very brilliant people, but very different people indeed. So through the whole of the story I'm going to tell you, I was there from 1963 onwards. Everyone knows about Martin Ryle. Peter Scheuer is less well known, but he was one of the most brilliant astrophysicists that was around. He was very modest. He did not push himself forward, but for me, he taught me almost everything I know about astrophysics. Now, one other important thing is that these people were all coming from a background in radar. They knew no astronomy. When I say they knew no astronomy, the first papers had the celestial coordinates back to front. So these people were engineers, electronic engineers, who wanted to understand what the nature of the radio emission was from the cosmos. Now, very soon after the first sources were detected, there were immediately two big challenges. Here they are. One was need to achieve much higher angular resolution, higher sensitivity, and the second was to understand the twinkling of all the radio stars. Just like the stars in the sky, the radio sources twinkle as well. And from the very beginning, Martin Ryle and Tony Hewish, they worked very closely together on both of this. Now, I'll show you the papers just in a moment. Now, it started off in a place called the Rifle Range, which was close to the Cambridge University rugby ground. Now, that's where all of the officers practiced their shooting. They were shooting, and there's a large area which was made available for doing radio astronomy. So here are some of the first aerials built. As I say here, there was no money. No money. So they had to use whatever they could find from anywhere. But one of the biggest sources of the equipment was from what I've called German war booty. After the war, the British armed forces went to Germany and brought back all the best equipment they could and stacked it all up in Farnborough in one of the military aircraft bases. And then Martin Ryle went and got for nothing radio telescopes, and in particular German coaxial cable, which was of extremely high quality, much better than British coaxial cable. So this was the source of what they did, and here we've got one of the first little interferometers that they built, and it's just coincidence that in the background is Martin Ryle's house. He could come out of his house and into his radio telescopes in 2 minutes. So this was how the Cambridge radio astronomy activity happened. And here is again a typical Cambridge fashion is Graham Smith and Martin Ryle building the first Cambridge telescope, which was a long Michelson interferometer. Now, just to show that, again, everybody was working together, because you need a lot of hands to build these telescopes, they were working on both the scintillation problem and the angular resolution problem. So from 1950, we've got this paper on, again, the effects of the terrestrial ionosphere on radio waves from 1960, Ryle and Hewish. Then we've got 1955, the Cambridge Radio Telescope. This is the 2C aerial. Again, the two of them combining. Again, the Large Synthesis Telescope, 1960, by Ryle and Hewish. And then the first deep surveys of the sky, again, Scott, Ryle and Hewish. So they were all working together on both of these types of problems. Now, I'll deal with Martin Ryle's great contribution first, and then I'll deal with what Tony Hewish and others happened. Now, I will claim that his genius was as an electrical engineer and being able to make very complicated and difficult systems work before anybody else could. Nowadays, this may look all trivial to do, but at that stage, there were no computers that were really effective for doing things. All the electronics had to be built by hand using valves. And it was really a big challenge to do all of this. Now, the big realization that the radio astronomers had was, let's look at how telescopes work. And this is for one of my public lectures, just to show how again, what happens. And of course, as you all know, the key thing is to make sure that the path length from the sky to the detector has got exactly the same distance and length in terms of wavelength. But what the radio astronomers realized, that actually you didn't need to get all the observations at one time. You could, in fact, block off most of it and leave just a couple of little telescopes there. And provided that you were able then to preserve the phase and for these two pieces, then you could eventually build up a complete big telescope by lots of little telescopes. This is the principle of aperture synthesis. But there were lots of challenges. And in particular, if you've got two telescopes which are going to track a point on the sky, then there you see the radio waves coming in, but you've got to flatten the wavefront. In other words, you must make sure that you've got all the signals coming in phase. So when you're far away from the two telescopes, you can see they're still in phase there, but you will notice that when you get close to the telescopes, there's a path difference which you must compensate for in order to make sure you combine all the signals in phase. That's the big challenge for these types of interferometers. Now, the way that was solved then, when you didn't have the electronics able to do it for you, which you do now, was that what you did was you put in a length of cable which was going to exactly compensate for this path difference to the other telescope. And then you would have flattened the wavefront of the two systems. But you can see the problem. You've got to keep switching in different lengths of cable all the time as the object is tracked across the sky. So it was technically a big challenge to make all of that work. Then you do cross correlations, and then you use computers to actually make the map of the sky. So that's the principle of Earth rotation aperture synthesis. And of course, if you've got lots and lots of telescope, it gets even better. You can got all the radio waves coming into there, and then you've got to put in all of the path compensation cables for all of the telescopes. So it's quite a technological challenge to do this. This is a 6-element interferometer, and you remember that the small spacings, the yellow ones, give you the large-scale structure, and the blue ones give you the fine-scale structure. So that was the big challenge. Now, you then want to get the two-dimensional structure, and that could be quite a problem. You'd have to fill a large field full of areas to do that. But then they hit on the idea of using the rotation of the Earth to actually move the telescopes about one another. So here's again my little cartoon. We are looking down from the North Pole, from Polaris, and we watch the movement of the two telescopes as the Earth rotates. And you all know what happens. What happens is that you see that happening, that happening, that happening, that happening. What you've done is the two telescopes have moved right about each other over 12 hours. So you actually swept out an arc, a complete circle on the sky. And let me just illustrate by this one here. Here are two radio telescopes, and as the Earth rotates and you're looking from the North Pole, then there's what happens. You've swept out the annulus of a big telescope. And so if you've got lots of telescopes, you can see what you do. You put that, you do the first circle, then you can move the telescopes or put in more telescopes. There they are there. Then you do that and you fill in the next one, and then you do the next one, and then you gradually you fill up the huge aperture by little telescopes and putting in all of these path compensations all the way around. It's a wonderful story. Now, again, this is electrical engineering of the very highest class using what was absolutely cutting-edge technology at the time. Now, the number of surveys were made. This is the 2C survey from 1955, which again was used to study deep, well, it's not no longer any deep, to make the first surveys of the sky. That was then followed by the much bigger 4C radio telescope, which is seen here, which did a very good deep survey of the whole sky. But the key one, which really started the huge development of the Earth rotation synthesis, was one by Martin Ryle and Anne Neville, who produced this map of the region about the North Pole. Now, the reason that was possible was because if you're at the North Pole, you don't have to track. You can simply point the telescopes at the North Pole. The Earth will take them round them. You can put in the path compensation and everything, and it will all work. And these sources on that map were a factor of 10 fainter than anything that had been detected by single telescopes. Jan Oort, when he came to Cambridge and saw this picture, looked at this and said, that's the future of radio astronomy, being able to use these techniques to actually do it. And that was the origin of the Westerbork telescope program, and all of the other telescopes then followed. Now, the technological challenges were very considerable. You had to be able to get the sine and cosine components of the incoming signals, and you had to develop phase switching receivers to be able to do that. The path compensation was achieved by switching in long cables at the right information rate to be able to get all the data for these rails. The fast reduction of the data was needed, and the radio astronomy group invented the fast Fourier transform to actually speed up the rate at which you could do the analysis. This was before the Cooley-Tukey work. And then there was the calibration, elimination of interference, receiver stability. And so all of these problems had to be solved to make this work. So what I'm saying is this was a real technological challenge. And again, I'm just echoing what people said this morning about the need for the technology to follow. Well, the first fully Earth rotation aperture synthesis telescope was the 1 mile telescope, which Martin built. And here it is here at the Lord's Bridge Observatory. And here are the first images that came out of the computer. I was there when it happened. I was in the computer room watching as the first aperture synthesis images came on. I saw this being printed out, and it just completely blew the mind. Here was at last, now the images of double radio source. This is Cygnus A. And even more spectacular, here was the complete ring of Cassiopeia A supernova remnant. And of course, this was again absolutely crucial because we knew now that this had to be synchrotron radiation. We knew huge energies were evolved. We knew that we had a very, very powerful sources of energy indeed. Then Martin went on to build the 5-kilometer telescope, again with 8 elements here, and it really was a tremendous telescope. Since then, it's been overtaken by other telescopes, but this is where much of the original astrophysics and the physics of the sources was studied. Now, the spectacular result of all of this, and this is really worth celebrating, in 25 years, the sensitivity of the radio astronomical observations had increased by a factor of 1 million. That's from the first observations made of Cygnus A just at the end of the war till around about 1975, when we were down to millijanskys and sub-millijansky flux density. That's a huge increase in sensitivity. And the imagery capabilities went from several degrees down to about 2 arc seconds, all in 25 years. Now that's really what, again, revolutionized the way in which you could actually use these observations to understand high-energy astrophysical phenomena. Another way of demonstrating that is to look at the structure of Cygnus A that was done by intensity interferometry by Jennison and Dasgupta in 1953 at Jodrell Bank. For its time, a wonderful achievement to be able to do that, but you can see it's very, very crude, and if you compare that with the map of Cygnus A now that we've got, it's the same source. You can see the wealth of data, the relativistic jets, you can see the hotspots, and this is actually putting together all the things we need for high-energy astrophysical processes. So it really is terrific. Now, I'm not talking about the astrophysics today, but just a quick summary of the impact upon astronomy and astrophysics, the discovery of the galactic and extragalactic radio sources. They really revealed the importance of relativistic astrophysics for astrophysics in general. And really, that was a key event in the history of astrophysics. There were enormous energies in relativistic particles and magnetic fields needed. Again, work by Jeff Burbidge. You were needing to convert 10 to the 6 solar masses of material into high-energy particles and magnetic fields. There's the role of the relativistic jets, which very soon it became apparent. The extreme variability of some of them, of the luminosity of these sources, meant that they had to involve supermassive black holes. And then, of course, the evidence for the cosmological evolution of the populations of the sources, which is stuff that I was involved with. And again, Rashid and I were working on that aspects of that when we were working in Moscow. So it really was a very major impact, and again, I think it's an amazing story. And again, Tommy Gold at the banquet in the first Texas Symposium made this wonderful statement once these observations became known. He said, "Everyone is pleased. The relativists who feel they are being appreciated, who are suddenly experts in a field which they hardly knew existed, and the astrophysicists for having enlarged their domain, their empire, by the annexation of another subject, general relativity." That's dated from 1963. So that's, again something worth celebrating. And as I said, all the big synthesis telescopes now use this sort of technique. Here's the VLA in the United States. There's the ETNF in Australia. There's the GMRT in India, and of course the ALMA array on the Atacama Desert. They're all using these principles of Earth rotation aperture synthesis. Now, going now back to the ionospheric scintillation problem, that was, again, very important in the early days because when it was working at a very low frequency, very low frequencies, long wavelengths, and there were these strong fluctuations, scintillations in the source intensities. Now, it was quickly realized that these were due to irregularities in the plasma density in the ionosphere, and Tony Hewish really took this part of the whole story on and worked out the theory in detail in 1951-52. These are the papers here, diffraction of galactic radio waves as a method of investigating the regular structure of the ionosphere. So that work was again central to understand how this worked. Now here's what happens. In this sketch here, I've got some plasma irregularities, and when the radio waves come through there, then of course they're deflected, and because these clouds are moving across the sky, then you get these rapid fluctuations in intensity when you observe a source. Now what Tony showed was that once he analyzed the details, these were structures on the scale of 2 to 10 kilometers at a height of about 400 kilometers high and moving at a speed of 100 to 300 meters per second. So this is indeed characterizing the ionosphere from the irregularities in it. A couple of years later, he actually noted in his notebooks that if the extragalactic sources were compact enough, then you would be able to see the structure of the solar wind by looking for the small variation inside. And here's the paper which eventually appeared in 1964, and you'll see here these scintillation pictures. So this is what you would expect if there was no scintillation, but in fact you see all of this structure here in these compact sources. And the other thing, for those who know their 3CR sources well, we'll see that these are all quasars. In other words, this meant that the quasars were compact objects which scintillated. So this was a challenge, and Tony then realized if he built a large low-frequency scintillation array, he could do these things. The small diameter radio sources were very often quasars, and so this was a way of finding many new quasars, and indeed that did happen when the array was built. You could also estimate their angular sizes, because once you'd characterized the interplanetary medium, then you could work out the size from the structure and how it varied over the sky. And then finally, you could work out the structure and velocity of the solar wind. So Tony received this grant of £17,286 from the Science Research Council in order to build this array to do these things. One of the key features was to detect the scintillations, one had to be able to observe fluctuations on a time scale of 1/10 of a second, and that was part of the specification of the array, which would end up being very important. Well, Jocelyn Bell, now Martin Bell Burnell, she joined the 4.5-acre project in October 1965 for her PhD, and her job was to build the array. And Jocelyn did a wonderful job. She hit the poles in the ground where you see these big poles. She had big heavy hammers to do it. And once that was built, then she had the job of actually being responsible for the cable network of cables which corrected all the dipoles of the array. So this is Jocelyn here in a bitterly cold Cambridge winter day, getting on with actually calibrating the array. Well, there it is. It's 4.5 acres or 1.8 hectares in size, and it just looks like a vineyard, something like that. But again, you could change the angle it was pointing on the sky by putting in different path compensations to do that. The other important thing was that the scintillations could be measured in real time, and that was terribly important. So this is an example of what you would see on the sky. You would just allow the sky to drift over the telescope, and you would get these sorts of traces here. Now you'll see this is one of the sources scintillating very, very strongly, whereas this one is not, that one's not. And so you then put this through a high-pass filter and get only the fluctuations, which you see here, and then you can average the power to get this signal here, which tells you you've got a scintillating source. So that was the way that things were set up. Now, another important part of the story is that Les Little and Tony Hewish, they then worked out how they expected the scintillation to change as you moved away from the direction of the sun, both in the plane and also going up out of the plane. And this was a crucial diagram for understanding what happened next. Here's the sun here. This is in the plane of the ecliptic. This is perpendicular to the plane. And on here, you can see the strength of the scintillations as you move outwards through the solar system. And in particular, the important thing is to note the very strong scintillations here, and they go down to less than 10% out at the distance of the Earth. So, what Tony told Jocelyn to do is every day they would be scanning the whole sky along a strip. So you see here are all the strips of the sky going from the equator up to high celestial latitudes. And every day, Jocelyn had to mark all the scintillation sources on this chart. Right? And the idea was, if they repeated at the same place, they were real sources. If they weren't, it was interference, it was a tractor, it was somebody else, an unsuppressed motorbike or something going along. So they had to do that. So this is one of Jocelyn's charts, and every time you see multiple sources together, that means it's a real source. So that was a very demanding task for Jocelyn, because the data was coming in at a fantastic rate. Every night you were getting 24 hours of data, and then she had to go and analyze them and put them on there. She did a wonderful job on that. The pulsars were discovered in CP 1919 on the 6th of August by Jocelyn. And it's interesting that in her PhD dissertation, which she was, by this stage, trying to complete very, very quickly, in her dissertation, the discovery of pulsars is Appendix 1, called Pulsed Radio Sources, and it's 2 pages long. The rest of the dissertation is all about the construction, calibration of the ray and the properties of the sources. And here's what was seen on that day. Here is again, just the trace here. This is interference. That will be a tractor or a motorbike. But here, this was the strange source here, which was scintillating at about the 100% level in the antisolar direction. In other words, it's something which should not have happened. It was scintillating very, very strongly indeed, and they realized that something was happening. Well, here's Jocelyn with that original record here, with the trace of the first pulsar to be discovered. Now, the source then disappeared, as many pulsars do, and then they tried again on the 28th of November with a much shorter time constant, and for the first time, here you see the pulses being detected. It consisted entirely of pulses with 1.33 seconds, and the stability of the pulse period was better than 1 part in 10 to the 6. It was an extraordinary discovery. Here it is. Here, let's go on. Now, the Cambridge Radio Astronomy Group had been burned in the past by not doing the analysis properly, and so they devoted a huge effort to absolutely making sure that this was correct. So all sources of terrestrial interference had to be excluded. If the source were associated with the next terrestrial emissions, including the notorious little green men, you had to be able to find out if the motion of the planet about the parent star would be observable. It would be easily detectable if it was, and it wasn't, and so that went away. The motion of the Earth about the sun was observed, but no orbital motion of the source. And in Christmas 1967, I saw the Christmas card that Jocelyn sent to Tony Hewish, and it was all pulses. And if you could disentangle the pulses, it said, "Happy birthday, Tony. Happy Christmas, Tony." So it's a nice story. The low-frequency signals display dispersion, and that means you could use the dispersion measures to get a rough distance of 65 parsec, And then, crucially, 3 other sources were discovered. And that meant they were onto something real. So it was kept under extremely tight wraps. At that time, I was in the room next door to Tony Hewish, where he was working, and I knew nothing about what was going on. They kept it so close to themselves. I only learned it when Tony gave a seminar about it 1 week before the publication of the paper. So they were just desperate not to make a mistake in doing these things. Well, the rest is history. The pulsars were then soon identified by Tommy Gold and presently by Franco Piccini as rotating magnetized neutron stars, and that's again the story. Now, the rest then is history. The discovery of the last stable stars, the neutron stars, which had been predicted, but nobody had guessed you would ever find these things by looking at low radio frequencies to look at the pulsed radio emission. It was one of these pure serendipitous discoveries because you had the new technology with a short time constant in the radio telescope. Very soon after that, large numbers of pulsars were discovered. Indeed, almost all of them not in Cambridge. We more or less came out of it after that first paper. The neutron stars were then discovered in binary X-ray sources in 1972, and then the famous Hult and Taylor discovery of the binary neutron star, which has provided these fantastic limits on the validity of general relativity. Well, that's the story of the way in which these technology innovations in radio resulted in, I think, very major contributions to our understanding of the necessity for general relativity playing a role in high-energy astrophysics. Well, the epilogue is as follows. Martin Ryle ceased to be involved in radio astrophysics after the completion of the 5-kilometer telescope. He became very seriously ill. He had a heart operation, and he had lung cancer as well, and turned his attention to wind energy and opposing nuclear energy and nuclear weapons. Tony Hewish continued the expansion of the ray and used the scintillation technique to do interplanetary weather. Jocelyn remains an extremely distinguished member of the UK science community. In June 2007, she was created Dame Jocelyn Bell Burnell. She's been president of the UK Institute of Physics and the president of the Royal Society of Edinburgh. So that is I think the point is just supporting what was said this morning, that technology is absolutely mandatory if we're going to actually make advances in general relativity and all the wonderful things, the ideas that we're hearing this morning in cosmology. They must all be linked one way or another to cosmology. And that's my message. Thank you very much.
Well, this was a passionate memory. Maybe the only thing while you were reading this sentence of Tommy Gold of the first Texas meeting, there was a person at the first Texas meeting who was sitting here, and he was convinced that this work would have been very important for the understanding of this phenomena. And this was Roy Kerr, who was present in that occasion. And we will ask Roy to make a recollection of his interaction with the system in those days. Well, thank you again. If there is any urgent question, please do that, and then we close, because otherwise these people, they lock and we cannot go out. Quick. But you were supposed to put the screen here. Why you did not put the screen here? You are going to put the screen in tomorrow. The screen. Yes, but tomorrow.